The last thing in chapter 2 involves more problem solving with the modulus function. So let's consider this example. We have a function p that maps x to 10 minus 2 times the modulus of x plus 4. Part A is to sketch y equals p of x. So this is a graph transformation of the modulus function. So firstly, note that if we had y equals minus the modulus of x, this would be a kind of upside down modulus shape. So we know we're expecting some sort of shape like this, but we need to translate this. So because it's the modulus of x plus 4, we need to translate this 4 to the left. We then need to stretch it, scale factor 2 in the y direction, and then we need to move it up 10. So we have this sort of shape which we would draw here. We're moving it 4 units this way, and then stretching it scale factor 2 in the y direction, and then moving it 10 units up. So the pointy bit is going to be located at minus 4, 10. Oh, sorry. Yes, minus 4, 10. That's right. So we have, this is up here somewhere. Let's work out where this graph crosses the axes. So if x is 0, so p of 0 is 10 minus 2 times the modulus of 4, which is 2. So we know it crosses the y-axis at 2. And if p of x is 0, then we have that 10 minus 2 times the modulus of x plus 4 equals 0. So the modulus of x plus 4 would be 10 over 2, which is 5. So either x plus 4 is 5, or x plus 4 is minus 5. And this gives us x is 1, or x is minus 9. So the two places it crosses the x-axis are 1. Sorry, this should be symmetric about the center here, but a little bit hard to draw. Maybe if I make this flatter. Okay, so that's 2, 1, minus 9. This is minus 4, this is 10. Okay, that's not the best sketch, but shouldn't really be feathered here. It's just I was silly and drew it in pen. Anyway, the graph should look this kind of shape, where this point is minus 4, minus 10, and it crosses the axes at these 3 points we've found. Okay, so that's the graph. Part B, state the range of p. Well, we can see that the possible y values on the graph are anything less or equal than 10. So the range of p is going to be the interval minus infinity to 10, including 10, or instead, if you prefer, you can write p of x is less or equal than 10, or y is less than or equal to 10. And then part C, explain why p inverse does not exist. Well, p is not a one-to-one function, so only one-to-one functions have inverses. Because p is many to 1, the inverse cannot exist. Okay, part D. Solve p of x is greater than minus 4. So this graph we've drawn helps a little bit, because if we were to draw a line, y equals minus 4, this graph is a complete mess now. Maybe I'll just redraw it. So we have this shape, and then we have this line, y equals minus 4. And there are 2 points of intersection. So if we can find those 2 points of intersection, it's in between those 2 points that p of x is greater than minus 4. So we need to solve p of x equals minus 4. So that's 10 minus 2 times the modulus of x plus 4 equals minus 4. If we move the modulus term to the other side and move the minus 4 to this side, we get 14 is 2 times the modulus of x plus 4. So 7 is the modulus of x plus 4. And then the two ways that the modulus of x plus 4 could be 7 is if x plus 4 is 7 or x plus 4 is minus 7. And that gives us 3 or minus 11. So this point has x coordinate minus 11 and this point has x coordinate 3. So the solution to the inequality p of x is greater than minus 4 is going to be in between these two values. So the solution is minus 11 is less than x is less than 3. That's the solution. Okay, and then on to part E. State the range of values of k for which p of x equals minus a half x plus k has no solutions. So I'll just again redraw the graph. Nope. So still not quite symmetric, but that will do. So something like this, and we had this line y equals minus a half x plus k. So I'll just draw the axes in here. So something like this. So y equals minus a half x plus k. That has gradient minus a half, so it's less steep than these lines, it's a bit flatter, and it crosses the y-axis at k. And we want to find the values of k such that these two graphs have no points of intersection. That's what it means for the equation p of x equals minus a half x plus k to have no real solutions. So we need the two graphs not to intersect. Well, there are a couple of possibilities for how many times they could intersect, because if we had something like this, they could intersect twice. And if k is anything lower than this, they'll definitely intersect twice. If k is up here, like this, they just intersect once at this point. And if k, this is k, isn't it? The y-intercept of this line. If k is anything higher, then they won't intersect at all. So we need to find the value of k that makes the line go through this point. And then if k is anything higher than that, the line won't meet the modulus graph at all. So, and we know what this point is. This point was minus 4, 10. So we just need to put that point into the line to find this value of k for this particular line, and then we need to let k be greater than that value. So if minus 4, 10 lies on the line, we put it into the line, so 10, that's y, is minus a half times 4 plus k. I'm sorry, I've just realised it was minus 4, not 4. So this should have been minus 4, which gives us 10 equals 2 plus k, so k is 8. So the answer is actually k is greater than 8.